Okay, let's get started for today's seminar. First of all, welcome to the research special seminar today. And so I'd like to thank our speaker today, and Dr. Rodney Askari,
Yes.
and he's from Michigan Tech. And thank you for coming, driving down here on a snowy day in Minnesota. And sorry for the very small accident. It's my pleasure to introduce today's speaker, Dr. Radwin Askari. And Dr. Askari currently is assistant professor at the Michigan Tech in the Department of Geological and Mining Engineering. And he received his PhD from University Calgary in Canada. And after receiving his PhD, and he worked as a postdoc fellow at the same university, but in the Department of Chemical and Petroleum Engineering. And before he came to the United States, came to Canada, and he was an instructor in the geophysics in the Institute for Advanced Studies in Basic Sciences in Iran. So his current research is focused on the environmental and the exploration geophysics. So let's welcome to Dr. Askari.
Thank you,
And
Dr.
today he's going to talk about the using laser array to assess the pavement structure, and similar to HWD, but it's not contact with pavement.
Okay. Thank you for giving me this great opportunity to present my proposal. So what we are going to propose in this study is a non-contact seismic land wave measurement of pavement structure using laser array. So in this presentation, first of all, I'm going to talk about the objective of this study. Then I'm going to review some concepts of seismic wave velocities and how they are linked to dynamic moduli. And then I'm going to talk about the method that you're going to use, this multi-channel analysis of surface waves, or MSW. And then I'm going to elaborate on land waves and how we can use them in order to characterize pavement. And then a little bit, I'm going to review some concepts of non-contact land wave data acquisition. And finally, I'm going to, talk about the method that we're going to propose for this study. So the objectives of this study is to develop a technique in order to a high and fast resolution technique to estimate different dynamic moduli of pavement. I mean thickness, stiffness, Young modulus, and Poisson ratio using seismic array. So using seismic array, what we are going to do, we acquire high frequency land waves. And so our method will be fast and doesn't require like stopping traffic. And as a result, so we are able to continuously measure elastic parameters of pavement. But I thought that we might have people with different backgrounds. So it is good to review some concepts of seismic waves. So we deal with the seismic waves in our daily lives. Acoustic wave that we communicate with is a subcategory of seismic waves. Our coordinate system is a seismic source that generates acoustic waves, and our ears are two seismic detectors that detect acoustic waves. Seismic wave can be divided into two categories: body waves and surface waves. Body waves are those waves that travel through the Earth's interior. They can travel through crust, upper mantle, inner core, and whatsoever. But surface waves travel along the Earth's surface. And because surface waves travel along the Earth's surface, they can provide us with information about near surface. Again, body wave can be divided into two categories: P waves or compressional wave. As you see here, the particle motion is parallel to the wave propagation direction. And so in other words, they are longitudinal. And we have the other category, that's S wave or shear waves, where the particle motion is perpendicular to the wave propagation direction, or we have transverse waves. Surface waves similarly can be divided into two main categories, Rayleigh waves that are generated as an interaction of P wave and S wave close to the surface. And as you see here, they have retrograde motion. And we have lob waves that is like a polarized S wave close to the surface. And again, similar to S waves, lob waves are transverse. So why, why seismic waves are interesting for us? Because using seismic velocity, we are able to estimate different dynamic moduli. What you see here, Vp is P wave velocity and Vs is S wave velocity. K is bulk modulus, G is rigidity or stiffness, and rho is density. So for any material, if we estimate P wave and S wave velocity using these equations, we are able to easily to estimate rigidity, Poisson ratio, and Young modulus. The method that we are going to use in this study is MSW method, the method that is widely used for near surface study and is very popular. The reason is that the method is very high resolution and also is straightforward. What you see here, we have a group of geophones that we deploy on the surface, and using a source that is really a sledgehammer, we generate surface waves. And by recording and what we do in the circle, we record surface waves. And if we record surface wave that can be Rayleigh wave, lob wave, or lamb wave, we are able to estimate P wave and S wave velocity of near surface. How? Just if you look at the equation, the velocity of surface wave, that is function of the frequency, can be obtained by Vs, Vp, rho, and H. That is S wave velocity, P wave velocity, density, and thickness of near surface layers. So for any Earth model, these two velocities, the velocity of surface waves is linked to the velocity of P wave and S wave. So in other words, if we record surface waves, and if we estimate the velocity of surface wave, we are able to estimate these parameters using an inverse or back calculation procedure. So here, I'll show you how this method works. First of all, we deploy some geophones that can record seismic waves on the ground. Then we record surface waves. Then using some mathematical tools, we estimate the velocity. As you see here, the y-axis is velocity, and x-axis is frequency. And the maximum value of this function gives us the velocity as a function of frequency. So once we estimate the velocity, we can estimate S wave velocity, P wave velocity, and density for near surface layers. So the method that is conventionally used for pavement studies is Falling Weight Deflectometer. And you're familiar with this method. The method is straightforward. What we do, we load a heavy weight on asphalt, and we measure the deflection. So once we measure the deflection, we are able to estimate pavement elastic properties using a back calculation procedure. However, different people are still working on this method in order to improve it, and they have criticized this method for some reasons. The major reason is that the back calculation of the method is not has a lot of uncertainty, and that's one of the major problem with this method. And another challenge of this method is that the elastic properties of this method is mostly affected by subgrade or subsoil rather than asphalt concrete. And that's another challenge with this method. And also, this method is really slow because we have to stop the vehicle, and as a result, we have to block the traffic, and we are not able to use this technique to continuously measure asphalt concrete elastic properties. So recently, a lot of people are working on this method, and that's lamb wave measurement or acquisition as an alternative to FWD method. And what you see here is an array data acquisition that is designed for land wave acquisition. And the technique of land wave is very interesting because land wave is high frequency waves, and there is less uncertainty in back calculation, more resistant to noise, and usually they provide higher resolution. So land wave is high frequency guided wave that propagates through plate structures. They have two symmetrical and anti-symmetrical modes. And again, like other surface wave, land wave velocity is directly linked to asphalt concrete dynamic moduli. And because land waves have high frequencies, they can provide with better resolution compared to reflection that is used in FWD. So here I show you how land wave works. So what we do, we acquire land wave using geophone. Then we calculate the velocity, and from the velocity, we can estimate different dynamic moduli, such as Young modulus and Poisson ratio. What you see here is a result of the study. What they did, they used two different destructive methods, and they compared the results with land wave measurement. And as you see, and what they did, they conducted the research for two sites of the studies called south side and north side. And the results of the values that they got from Young modulus and Poisson ratio was close to those obtained from destructive methods. So here I want to give you like short history. The first research on land wave was conducted in 1993 by a group of researchers at the University of Texas in Austin. And what they conclude, so that research was led by Awad. And what they did, they said that there is less uncertainty in estimating dynamic moduli and higher accuracy in the depth of bedrock. Following them, another group of researchers from the University of Texas in El Paso showed some promise of land wave acquisition for studying pavement. And more recently, Radwin from Sweden is working on this method very hard, and he has published a lot of works on land wave acquisition. However, there is a challenge with land wave acquisition, and the challenge is that land wave is high frequency waves. So in order to detect it, you have to have a strong coupling of geophone with asphalt concrete. And so if you want to have a strong coupling, so it means that the data acquisition can be very slow. And in order to address this challenge, different people try to somehow develop new acquisition system. For example, one research that was conducted at the University of Iowa State University Department of Civil and Construction Engineering by Lin and Ashlock. So what they said that, okay, instead of using several geophones, we can use single geophones, but instead of having one shot, we can have multiple shots at different locations. So what they did, they said that, okay, we use one geophone, several shots, and if they do that, they're gonna somehow reduce the time for coupling of geophone, and they call their method multiple source one receiver. And actually they compared their method with conventional MSW method. As you see here, that's the data that they acquired using their method. That's the method that data from MSW method, and that's the velocity, the velocity of land wave. As you see here, the velocity they were able to obtain the velocity for low frequencies. For higher frequencies, they weren't able to get the velocity. And the major reason is that their source is not any seismic source is not 100% repeatable, and for that reason, they weren't able to get good high frequency component. for the data acquisition. And those high frequencies is extremely important, especially when we deal with asphalt concrete, because they can provide us with good estimate of elastic properties in asphalt concrete. Question?
What was the sensitivity of the receivers?
Could you repeat the question?
The sensitivity of receivers.
Yeah, I mean, that could be an issue with MASW. High frequency phones or accelerometers? Or...
Yes, they use accelerometer.
They did. Okay.
Yeah. So if you look at here, they said accelerometer. That's what.
Oh, I'm sorry.
But recently, people are trying to obtain non-contact measurement of land wave. Again, Radwin's group in Sweden, what they propose that we can use microphone as a seismic receiver. So what you see here, they install an array of microphone close to the surface, one centimeter or 2 centimeters below above the surface, and the vibration of land waves can be transferred to the microphone by acoustic waves. And they propose that this method can be very fast because you don't have to care about installation of geophones over the surface. What you see here is the trolley that they made, and this is the microphone array. So this trolley is mobile. So what you're going to do, they said, okay, if we have such a data acquisition, we are able to have mobile data acquisition, and as a result, we can continuously measure different elastic parameters of pavement. And that's the land wave that they acquired using their setup. So what you see on left is the land wave data, and this is the velocity of land wave using their setup. And what you see on the left is the results from accelerometer that they use as a source in a conventional geophone. And that's the velocity. So as you see, the velocity for the two cases are quite compatible. And they get very good results. They get very good results from their acquisition system.
What's the source?
The source was like a small screw, because the source should be high frequency.
So you have just static.
A screwdriver, sorry, screwdriver.
Stopping there to...
No, they move it. They said that what they did, they added the mobile data acquisition by watching the speed, watching the speed.
So the source is a laser wave?
No. The source that they use is like a screwdriver. Once they tow it, it hits the surface.
Scrap on the surface.
Yes. However, their method is very sensitive to the roughness of surface. And the major reason, the acoustic wave travel very slowly compared to land waves. So any unevenness of surface is going to create some delay for acoustic wave to get, for example, here to the microphone. And they said that, the roughness can introduce a lot of error for their data acquisition. However, they propose that if they have back and forth data acquisition, they might be able to address this challenge. So what we're proposing here is to use laser as a seismic receiver. Laser has been used as a seismic receiver many years ago, like about more than 20 years ago, by Bernie, who was like an employee in Shell. So how we are able to use laser? So the vibration of the surface initiates a Doppler frequency shift on the reflected beam of the laser. And that frequency shift is proportional to V. That V is the vibration velocity of the surface. So in other words, if we measure the Doppler frequency shift, we are able to estimate the vibration of the surface. And that's the methodology that was introduced in order to use laser as a seismic receiver. What you see here is the setup that was developed by Bernie in order to use laser as a seismic receiver. And he used his method in order to take different vibrations. And so the major reason that Shell was interested to use laser as a seismic receiver, because sometimes oil companies don't have permission to install geophone at specific location, for example, because there is a private property and the owner doesn't allow for any data acquisition. So they wanted to make a system to remotely be able to remotely acquire seismic data. So they put their laser system 800 meters away from the target, and they tried to record seismic data using geophone that indicated by geo here, and laser system that's LDI here for different targets, as you see here. In all cases, what they got from their data, their record, are quite similar to what they get from geophone data. For example, for dirt, you see that this record by laser, by geophone. For sand, you see again this record by geophone, and we have laser. The only thing that they didn't get good results for rich water. However, for again calm water, they got very good results. So the results were very promising. So why we are interested to use?
From your input to your output, I think you're learning mathematical filter.
Yeah, so we have to do mathematical filter for.
What filter? Hanging window
and
what window in algorithm?
Oh, so yeah, so the response function of geophone is different from the response function of laser. So you have to multiply that response function to a window to a filter function in order to make the same the response function identical.
Okay, so that's a transform.
They transform it.
So what's the transform?
They didn't go to that detail. They just say that they mostly talk about the Doppler frequency shift in the paper. Yeah. So why we think that the laser is better? The first thing that the laser signal is much stronger than microphone signal. The second that this laser is not affected by acoustic background noise. And because the speed of light is very high, laser is more resistant to the roughness of asphalt in the case that we have a lot of roughness for asphalt concrete. And so for that reason, we think that laser is superior compared to microphone. So in our department, actually, we run a data acquisition to see if the acquired land wave, if the data that we got from laser is comparable to geophone or not. So we deploy some geophones on the surface, as you see here. And we have a laser system here that is opt-met scanning laser that's used to detect vibration. And using a sledgehammer, we generate surface waves, high frequency surface waves here. And just we wanted to see if the record that we get from our laser is comparable with the data from geophones. So what you see here is the data that is recorded by the geophone array, but one of them is laser. So is there anybody who can say which one is laser? Or no, blue one is just for other purpose. Yeah.
The middle one, right? Put in the middle.
Yeah, it was something in there. Actually, so we asked this question with different geophysicists, and no one was able to answer this question in our department. And indeed, that's the data, that's the case by laser. And as you see, it's almost had the same feature of other traces by geoforms. So we're going to use a laser array with more six lasers in order to make better comparison, especially when we estimate the velocity to see how the two velocities that we get are, close. So, but so far with just one laser receiver, we got very good promising results. And so it's our team that they are collaborating with us in this project. So we have Dr. Susepi from Mathematical Science Department who's going to work on seismic wave numerical modeling. And then the major challenge of this process, so we know that once the vehicle the vehicle has a lot of vibration. And so in order to be able to detect land waves for fast acquisition systems, so we have to do some motion compensation signal processing. So we have Dr. Michael Reigeman from the Department of Electrical Computer Engineering and Scott Wanger from School of Technology. And we have Dr. Jianping Liu from Department of Civil and Environmental Engineering, Dr. David Nis from Physics Department, who's going to help us with laser analysis. And another component is like to design high-frequency seismic source, who's going to Dr. Roger Terpening will be working on that. And we have Alison Hain, who's going to be our financial affair. Okay, thank you for listening to my talk, and I'm ready to answer your questions.
Questions?
A very nice presentation. One question is, do you have a feeling for how the high frequency source is going to behave in terms of attenuation? Are you going to be able to get the necessary wave propagation distance to get your multiple receiver signals?
Yeah, so that's a good question. So because it's high frequency, we're going to have less depth of penetration. So if you want to characterize pavement, the length of acquisition should be 1 meter. And so even if the frequency is very high, I think it's going to be enough to, for 1 meter, it's going to be enough. It's not going to, attenuation won't be very high.
Have you tested it on asphalt yet?
No.
Yeah, to what extent would this technology assist with the process of evaluating pavement condition? We want to know, in most cases, what's the hidden level of degradation that will not be obvious on the surface. To what extent can this be transmitted into that mode of information gathering?
So your question is that how we can...
How can this help us in evaluating pavement condition? In most cases, the degradation that we have are not sufficient. They are subsurface. So how can we use this to detect how bad, for instance, if you have stripping in asphalt, which you can't see from the surface, or trapezoidal degradation of concrete at the joints, which you can't see from the surface. How can this help us with that type of pavement condition monitoring?
Okay, so using the method, we are able to estimate different elastic parameters of asphalt, concrete, base, and subgrade. And if you use the full waveform inversion, or like more advanced technique, even you're able to, detect delamination. And so I think, did I answer you correctly, or you're talking about how we can validate?
Well, because what I saw you do was talk about some basic mechanical properties, talking about Poisson's ratio, elastic modulus, and so on. In most cases, we are looking for an indicator of degradation. Layer modulus may have a more pertinent representation of what we're talking about. But can you tweak this into something that can quickly give us, when we sweep it across, instead of affairs. That's what we want to know.
Yes, definitely. Yeah, that's a good question. So you have some criteria that you use for falling weight deflectometer. Okay. So the values that you use, and you know that, for example, this value is the stiffness, and so because it's not good for asphalt. So we can use those criteria in order to validate. So once we have your measurements, for example, you have for asphalt condition, then we can estimate those elastic properties and link them to what we measure here. For example, this condition is not good. If the elastic parameters are in this range, so it means that the asphalt condition is poor. So there are some tables for FWD method.
I think another question is, can you get the thickness of asphalt layers?
Yes. Yeah.
How?
So as I said, so once so what you see here, one of the main parameters is H. So the thickness of, so it is like function of H, VS, VP, and density. H is thickness of asphalt and base. So it's like a multi-unknown question.
Right?
Yes.
So I don't deal with a lot of land waves or guided waves, but based on everything I've seen, it looks like they do have dispersive qualities. Is that right?
Mm-hmm.
So getting back to Bernard's question, if you wanted to make it, you can make a 2D profile of what you're seeing with this data, right? So you could actually see the stripping in there from be it low velocity zone or something like that, correct?
Yes.
Okay. Trying to remember what my other question was. Somebody else have a question? I'll think of it as such.
So my understanding, the land wave and the rally wave is based on thickness. Land wave is basically on plate, traveling plate. So is there any minimum thickness between the land wave and the rally wave for the pavement thickness to be able to variable to use the land wave velocity?
Okay. Now it depends on frequency. So the more high frequency, so if you mean that the thickness, so it means that if you have higher frequencies, so if you generate low frequencies, you're going to have low waves, because Rayleigh wave, because Rayleigh wave cannot see those thin layers. But in order to generate land waves, because they just play their high frequency, should have like high frequency source. So one of the things that we have to address in this proposal is like to have a good high frequency source.
So high frequency, you have the shorter wavelengths.
Yes.
So they will not be able to see the deep in the tables, right?
So it has a range of frequency. So when we talk about land wave, it doesn't have like single frequency. It's a range of wavelengths. It has like range of.
So then you need to pick up which frequency you can look at based on the thickness of tables.
So if you look at. So if you see, like they have dispersion behavior, it means that high frequencies usually provides information about near surface. Mostly asphalt. When we go to lower frequencies, usually give some idea about, deeper layers such as subgrade. So we have to take all range of velocities that we get into account in order to get the good estimates for different layers.
Professor, I have a question from somebody online in Illinois. What would be the operating speed of the vehicle during testing?
The velocity, the speed? I knew that somebody might ask this. So right now, I can't say anything right now. So what we're going to have to test it. And definitely that work requires a lot of signal processing. And it is better not to say any number right now, unless we can test our method.
So that question kind of relates to mine. My question was what's the next step? Are you going to take this to a field site and do some field trials on pavement sections and compare it to other available technology?
Yes, so definitely once right now, so we're waiting for laser array in order to measure. So the first thing that we are going to do, we are going to, make all parameters established for static. Once the vehicle is not moving, then after that step, you have to, go for thrusting, just going by a slower speed, then increase the speed, and how different thrusting step you have to apply it on data. Yeah. But necessary will be measuring asphalt elastic properties.
All right, so I remember my question. And it gets back to the dispersive characteristics. You probably noticed the dispersion analysis is the key part of anything.
Yes.
Whether it's MSW, it looks like this is the same thing. And I'm looking at your figure there. It looks like you may even have some higher modes in there.
Yes.
So you deal with mode corruption just like MASW would. So how would you get around that?
Okay, so actually the technique that there is a technique that was introduced in about I think 2010. I'm not sure, 2006. And what they do, in order of just picking the velocity, they deal with the entire fixed velocity. So they take everything for inversion. And so for that reason, you don't have to even pick different modes. You would take the entire spectrum and take it to inversion. So for that reason, you have to do full waveform analysis. And for that reason, I think that this method gives, if you incorporate higher modes in your inversion, so you're going to get even better results. You don't have to, also you don't have to train, the technician in order to pick different modes. So we want to make it automatic. If somebody has a little experience, they can,
So there's no issue with overestimating your velocity or anything like that, which ultimately could mess with your stiffness.
Yes, I think that if we take all the higher modes in our inversion, we can, minimize uncertainty.
So over the length of your array, if there was some variation in thickness of the asphalt, do you have a feeling for how much that will add additional noise to your data set and how you might handle it?
And so this method depends on, how you want to invert the estimated phase velocity to your model. So if we use full waveform inversion, we can take into account different variation. But simply, for 1 meter of length, the easiest way just is say that what we are gaining as output is an average of the thickness for that 1 meter of length of array that we have. So if you use full waveform inversion, we can, see the variation. But if we want to make them, the computation simpler, so we have to say that, okay, make an average. Yeah. So what we get in terms of thickness is thickness for 1 meter, average of for 1 meter length of array.
So speaking of noise, how well does this work? How do you think this will work in a field setting, a construction environment where we've got trucks going by and all sorts of things, and putting noise into the ground and whatnot?
I think because the range of the frequencies that we have is high frequency, the frequency spectrum of the noise is different usually. By construction, about 30 hertz, but we deal with frequencies more than 100 hertz. So I think we can filter those background noise.
More questions? I have the last one, not in this acoustic, this non-wave field. But then for the geoform or the laser, you record this displacement. Basically,
yes.
It's surface displacement, it's vibration.
Velocity.
Velocity. How from velocity you extract for the non-wave from the time history wave?
So so how we can,
how did you calculate the land wave from this velocity wave?
so the particle motion is due to the land wave.
Yeah.
So that's what you record is the velocity of particle motion by land wave.
Okay, that's velocity is land wave velocity.
Okay, so geophone, measures velocity. So if you make an integral over velocity, you can get displacement. And if you make like, if you drive, you can convert velocity to accelerometer. So it is not very important if you measure the velocity. What is important for us is these dispersion curves.
Any more questions? Other than that, thank you.
Okay, thank you very much. Thank you for giving us opportunity.